All right, guys, as I look at number 45, I'm almost concerned that they didn't give us enough information to do this problem because usually I'm looking for four things. Two functions, which we do have here, and then usually both a left and a right bound here for x, often given to us in the form of an interval. But I got a funny feeling here that as soon as we graph this region, we might realize that we have everything we need here. So let's take a look and see what's going on here. We've got the graph of y equals sine of x, which I certainly hope by this point we all know pretty well. Come on, there you go, passing through the origin, right? Let's see. Now, I'm not going that far with this thing. It comes up and over like this, and that occurs at pi over 2. We're only graphing this thing until pi over 4, so that's actually more of the sine graph that I need right here, guys. And of course, it's going to do the same thing on the other side here as well, but I don't know that I need any of that at all. Now, the graph of cosecant squared, I actually just did that in a video that I made about, nope, I lied, that was secant squared. So let's try that again. The graph of cosecant squared. Well, what we're looking at in blue here, guys, is the graph of y equals sine of x. Cosecant is the reciprocal of sine. So let's talk about how we might come up with the graph of cosecant of x. I'm going to do that in green. And cosecant just being the reciprocal, well, let's take a look. For example, at pi over 2, right here, guys, when sine is 1, cosecant is the reciprocal of that. It would have the exact same value here. Then, at the origin right here, where sine is 0, cosecant is the reciprocal of 0, which is undefined. That means we're dealing with a vertical asymptote for the graph of cosecant. And then, if I read my sine graph right here, guys, as peaking at 1 and then coming back down towards 0, that means that its reciprocal is going to go the opposite direction. It's going to start at a trough, a low value of 1, and then head on up towards infinity, looking something like that. So that in green is the graph of y equals the cosecant of x. But wait a minute, we wanted the graph of cosecant squared of x. Now, as I did talk about in this problem, number 11 here, the graphs of secant and secant squared are really pretty much the same, at least in the part that we're looking at right now, and more or less the same thing happens right here. All of these values we have in green for cosecant of x, well, let's take a look at them. They start at 1, and when you square 1, you still get 1. As I move to the left now, going in this direction here, guys, my cosecant values were all positive and greater than 1. As I square numbers that are positive and greater than 1, what happens? They're all positive as well, and they get bigger just a little bit faster. So the graph of cosecant squared of x probably increases like this, but still ends up going in the same direction. So that in purple is going to be the graph of y equals cosecant squared of x. Okay, so that's what we're looking at right here, everybody. And again, they just wanted this thing going now. Okay, I get it. Here we go. Starting actually at pi over 4. So pi over 4 is going to be right about here. So in red, I will extend that upwards, not as an asymptote, but as like a border that's doing that. And now I see what they want, guys. They want the area of this little triangular region right there. It's bordered by pi over 4 on the left, cosecant squared of x on top, and sine of x on the bottom. So I didn't realize that's what they were asking for right there until I actually graphed this out. So let that be a lesson to everybody here. We got to get a good graph in order to work this one out. Okay, this is going to be a dx problem, guys, because no matter what rectangle we draw here, it's going to be bordered by cosecant squared on top, sine on the bottom. So area is going to be a definite integral here. I'll do the limits in a second of the top function, which is cosecant squared of x, minus the bottom function, which is sine of x, all taken with respect to x. Okay, so that's where we are right there, and the limits of integration would need to be the lowest and highest values of x in this region. Well, it begins right here, guys, at pi over 4, and it looks like it ends right here at pi over 2. So that's what I'm going to put there for my limits, from pi over 4 on the bottom up to pi over 2 on the right. Now the question for all of us would be, does this look like an antiderivative that we can evaluate by hand? And at first glance I thought no, but now I may be remembering something here, guys. The derivative of Let's take a look right here. Where do I want to write this? The derivative with respect to x of cotangent of x, everybody, is negative cosecant squared of x. That's going to work for us here. So area equals antiderivative of cosecant squared is going to be the opposite of the cotangent of x. And then minus antiderivative of sine would be negative cosine of x. So that's going to become a plus cosine of x, and that should be our antiderivative. Let me think about that real quick. The derivative of cotangent is cosecant squared, so negative cotangent's derivative is positive cosecant squared, and the derivative of cosine is negative sine. Yeah, I feel pretty good about this. Okay, so that's where we stand right now. Let me put my bar at the end here, and we're going from pi over 4 to pi over 2, and here we go. Boy, I just keep creeping further left here. Area equals, and let's put in the pi over 2 first. I'll write this out. Opposite of cotangent of pi over 2 plus the cosine of pi over 2, that's what we get first, minus the opposite of cotangent of pi over 4, and then plus the cosine of pi over 4. Okay, that's where we're at, and let's take a look at what's going on here, guys. Cotangent at pi over 2. So I'm going to go back to my unit circle right here and see where we're at. At pi over 2, which is right here, that's the ordered pairs 0, 1, tangent is y over x. That would be 1 over 0, which would be undefined, but cotangent is the other way around. X over y. 0 over 1 is going to be 0, and I don't have to worry about the opposite of that. Plus cosine, which is our x-coordinate at that same angle, which is going to be 0. Well, that wasn't bad. And then minus, let's see where we are now. Pi over 4, now we're at this angle right over here with a 45, 45, 90 triangle. Tangent right there is going to be 1. Cotangent is as well, but the opposite of that will be negative 1. Gotcha. And then plus cosine of pi over 4 is going to be root 2 over 2. Okay, that's where we're at here, guys. So let's see if we can't clean this up, but I think we're one step from being done. I can ignore all of that. Distributing the negative now, that's a positive 1, and then minus a root 2 over 2. Well, if we can think of that 1 as 2 over 2, you know what? I could have left that answer the way it was, or I could write it as 2 minus root 2 over 2. Any one of those would be fine. So it's not a real clean answer, guys, but that's what we get here. So I'll write it that way, 2 minus root 2 over 2, but you also could have left it as 1 minus root 2 over 2 square units, and that would have worked as well. Either one of those is the right answer then, or an acceptable right answer, I should say, for problem number 45.